I program with mobile apps, and recently, that's to say in the last 3 years, I went from a world in which how do I put it? Everything we did was fine and people got upset if we made mistakes, but fundamentally nobody lost any money. And then we went quite suddenly into a world where we were doing not just banking apps, but apps which were transferring money and actually delivering, sort of making cash payments. And I found that highly scary. I can tell you, the thought that someone might sue you was particularly nasty. And the thing that I found most difficult was this weird encryption kind of mysterious world. Now, this will be familiar to about 30% of you, so bear with me. Think of this as a synthesis of what we know. But it's this really complicated world of encryption that seems to be arcane and quite frankly, the literature gives you the impression that it's intended to be like that it's intended to be obscure and that the complexity is built in. And it's taken me quite a while to realize that actually, no, that complexity is not built in. The fundamental 5 principles of cryptography are very, very simple. There's lots and lots and lots of complex stuff about attacks on those things and how you might do them wrong, but actually the 5 principles, the 5 techniques that cryptographers use, most of the time, I'm sure there are others, but most of the time are very, very simple. And in fact, they have to be very, very simple, because if they weren't very, very simple, the mathematicians wouldn't be able to prove that they work. So, you know, the maths would be so complicated that you wouldn't be able to do anything with them. So, for this talk, I've got together the 5 key Bluffer's Guide things to cryptography, everything you need to know in order to put together a cryptographic solution. Well, not everything, but the main principles you need in order to design a cryptographic solution. And the first one is so mind-bogglingly simple, I couldn't think why it's not just obvious, which is the idea of a key. And a key is a surprisingly short hexadecimal, a string of digits. Typical keys are about 34 bits or something. That's really not, 50 bits, really not very long. 1 to 8 bit encryption is standard, but that represents, by the time the complexity is done, about rather less bits. And 1 to 8 bits is not very many characters. And the principle is that if you've got that number, 2 to the 1 to 8, is a number so large that you can't just go through all the possibilities. It's random. So if you think about the key in your pocket, that actually probably only has about perhaps 500 possible combinations, 500 possible keys, not much more than that. So when you get to 2 to the power of 128, you are talking about the same sort of principle, but such that even a computer cannot just try out the pick locks, cannot try every combination. And that's the fundamental principle of cryptography, that a key is very difficult to find out by brute force. Oops. So, the simple use of a key is you use it with some sort of mathematical process to encrypt whatever it is you want to send, whatever it is you want to keep secret. And the simplest, this is the next principle, the simplest form of encryption, conceptually, is called symmetric encryption. Is this familiar to everyone? Symmetric encryption? Some. Okay. So the simplest form, I encrypt something, which means I use a mathematical process on this. It's actually, I've written it, and I've written some of the basic cryptographic algorithms. At one point, Symbian let us down, and Nokia suddenly removed the encryption algorithms from the operating system, and we thought, oh no, we're completely stuck. And then discovered that actually it only took us about half a day to write them ourselves. It's not the writing of them that's difficult, it's them proving that they work. So you encrypt it. Basically, you take the message, you mangle it in a mathematical form that uses the key, you come out with a string of random looking bytes. Bob, Alice, my other friend, uses the same key to decrypt it. And that's called symmetric encryption. Very simple. Pretty much the fundamental thing that's going on in almost all forms of encryption, symmetric encryption. That's great, but as we know from the last session we had here, the business of distributing the keys is complicated. Who was here for the key signing party? Yeah. Sharing keys, trusting keys is a very complex operation. Is sort of conceptually complicated. It's fine if we're in the same room, fine if I can just hand you something that you then take away, but as soon as you get further away, that's more difficult. And so we enter public-private key encryption, the other sort of encryption. So here's an example of public key encryption, which is the idea of a mathematical relationship such that in fact they're based on that two keys are in fact two prime numbers, and it is based on a mathematical identity that if your prime number is long enough, it is quite difficult to factorize the multiple of those two. That's about all that's going on. Some of the more modern forms of encryption use other relationships, but the classic one, it's the idea these are two prime numbers. If you have a number that is the multiple of the two, it is very difficult to factorize. So with this one, you have a public key which you can give to anybody. So I can hand over my public key to all of you, and no security has been compromised. Then you use that public key to encrypt something, and you can send it to all of us, but I'm the only person with the private key. So I'm the only person who can decrypt it. Or in this case, Alice. I'm Alice for this purpose. I'm the only person who can decrypt it. So again, there are various different algorithms, various different flavors of this, but that's what's going on. Now, the next concept takes encryption but uses it for a rather different purpose. So this is to deal with the message. I've got a message, I've sent it to you. We could send it in clear, we could send it encrypted, it doesn't really matter. How do you know that the message came from me and wasn't someone else pretending to be me? Electronically, normally you'd have a signature at the bottom or something, in law you'd have a signature so that I could look and I could say, yes, that was me. In the computing world, what you do is you take some form of hash of the whole message, so you munge the whole message together in such a way that changing a single character would change the hash in pretty unpredictable sorts of ways. You then encrypt it with, because I'm sending it, I then encrypt it with my private key, and I get a sort of, something like a few dozen bytes that I'll add to the end of my message. And then you, Bob, when you receive it, you take the message, you do the same hash on it, and then you check that when you decrypt the hash I've sent with the public key I've given you, you end up with the same value. That's message signing. And that doesn't do anything for the security of the message, but stops someone else spoofing and pretending, getting, what's called man-in-the-middle attacks, where somebody takes your message, changes it, or simply sends another message, and you can't tell the difference. So that's fine so far. We then have the problem that how do you identify someone you've not met? So I want to send a message, but I have how do you know? I can't send you the private key, I can't send you my public key because you can't trust that the baddies aren't going to get in the middle and take that public key. So I've got no way of distributing my public key to everybody in a way that we can trust, unless we actually all meet together, as we did in the last session, and hand over manually. And the answer to that one then is this signature chain, various names, where you have one person you trust that provides what's called a root certificate. Effectively, that's a public key plus some other data. That root certificate owner, using that private key, can then sign someone else's. You then sign a root certificate for, say, me. In practice, you'll do 2 or 3, so someone else who can then sign for me. And then you have and each time, each of those signatures can be verified because they've got public keys in them. But the only people who can create them are the people who own the public key, people who own the private keys. So that goes right the way back to me, who owns my private key, and I can give you a chain here. And so long as you have got this root certificate somewhere, and they are generally shipped with browsers or with phones, a whole lot of these root certificates from companies like VeriSign, then you can be sure that if I send you a private key along with this chain, no one else could have created that. Sorry, if I send you a public key along with this chain, no one else could have created that public key. So it's got to be me. Now, I'm sure there are people here who can tell you the weaknesses and all that, but it's considered secure enough for most financial purposes these days. That's key signing, signature chains. So we've now got a way of distributing those public keys to everybody, and that basically is it. There's my 5 Bluffers Guide to Cryptography. There's lots of combinations of all these things that add together. For example, there's HTTPS. Now that has many different variants, but the most common one, which is the TLS protocol underneath it, you use all of these things. So when you make the first message, you validate that you've got the right server using a root certificate in the thing, and you go and ask the server for their certificate and check using that certificate chain that it's the right server that's giving it that. No one else would be able to give the right certificate and get it in a form of the chain that it does. So you can check that. The client, the web browser, then generates a random key, just using a random number generator, and it passes it to, generates a random key. It then what it actually does is it passes it to the server. The server then encrypts it with their private key. You can then unencrypt it with a public key. So we now have a situation where we both have this random number, and we've both got the same magic random number at both ends, and we can then use symmetric encryption, which is much faster. So the only snag about public-private key encryption is that it's slow. Takes a lot of maths. So what you really want to do is to move as quickly as possible to something like RC4, which is fast symmetric encryption. So you've put together all those 5 concepts, and you've got HTTPS. And pretty much as far all of the cryptographic techniques I've seen are combinations of those 5 simple root principles. I knew all of this before, and dead easy. Yeah.
What you're talking about there, is that the key exchange protocol?
Sorry?
Is that the key exchange you're talking about there?
For the yes,
Yeah.
it's one of them. It's the TLS key exchange. That's right. So it's that random key is then exchanged. Get it.
Going back to the banking applications, when you have your card reader, what part is that? Is that something to do with creating your public key that generates a random number that...
Your card reader, in your card, that you will see there's a little chip. It looks a bit like a phone SIM actually, and indeed has the same electrical connections. In that little chip, there is there's probably more than one, but fundamentally you can think of it as one encryption key. It's actually, for historical reasons, a symmetrical encryption key. It's not a they don't use public-private encryption very much, and that was because until quite recently the computers on the cards weren't very powerful. So you'll find that but that's what it is. So effectively all you're doing is carrying around a little key that is unique to you. So when you do some transaction or other, the machine, the merchant's machine passes a message into your card. The card then generates a signature using, then signs that message using your private key, sends it back, sends a signature back, and the merchant can then go through the internet and just check, yes, only you could have generated that because only you have that private key and of course the card manufacturer. So so in fact you can think of all of your cards, your bank cards, etc., just as ways of holding a private key. Ways of holding a symmetric key.
So your private key goes to the card reader, your own personal one at home, and then you get a random code.
Yes.
That's a public key.
That
would then allow you to set up a transaction.
That is actually a signature.
Right.
That what it's doing is it's taking something. So, for example, when you use it to log on for banking, you put it in some sort of machine and you type in one number and it munges it and it comes out with another number. What it's doing is encrypting it and telling you a few digits from the encryption. And it knows that only your bank has got the same encryption key and can come out with the same few digits.
It's also using the clock as well.
And then there's some cleverness with the clock, isn't there?
So that it can only happen, it's only valid within a certain period of time.
Yes.
So the
Yes.
clocks have to be synchronized, which is why eventually they'll fail because the clocks come out of sync.
Yes. So again, in each case, the hard bit about this sort of security stuff is thinking what the baddies might do and thinking how you can use these techniques to defeat all the things the baddies might do. So there's all sorts of attacks like
It's not uncommon also for businesses, corporations to install their own root certificates in the browsers so that they can monitor HTTPS traffic over the network.
Yeah. Oh, I see.
Yeah, when you
Yes.
sign a certificate.
Yeah.
Oh, yes, and then they have a
You have
gateway.
your own-
Yes, so that they can,
Yeah.
so that you do HTTPS to the gateway and then on out, so that they, yeah. There's
Should I design my own encryption scheme? just asking that for the benefit of everyone.
unless you are an extremely anal mathematician, I would suggest not.
And even if you think you are, you shouldn't.
When you were re-implementing the removed algorithms from Nokia, did they remove them for a reason?
Yeah,
No, I don't think so. It was a weird thing. It happened, between two very minor release numbers in the cycle. It was completely unexpected, and I don't think they did. I think they just restructured it in some way and didn't need it.
Was it ROT13 you were using?
No, but that was an early Symbian encryption technique. Yes.
Take half a day to
Yeah.
do that. So.
Yes.
Any more questions? Okay, thank you very much, Charles.
Thank you.
Thank you.